Good day! So for this learning task, we're going to provide the mechanistic steps of a 10-step synthesis stipulated in a research article. So without further ado, let's begin. So this is the research article that I chose, the fluoridated sparfloxacin as a new photo product identified by liquid chromatography coupled with UV detection and tandem mass spectrometry by Engler et al. So this research article includes a 10-step synthesis of a reference compound, which is the defluorinated sparfloxacin, wherein one of the fluoride atoms of the sparfloxacin compound is replaced with an amino group. So this is the overall synthetic route that was taken into turning this starting compound here into the reference compound, which is the defluorinated sparfloxacin. Now we're going to digest this synthetic route per reagent so that we could see the things that had transpired per reaction. Now first is the reaction of the starting compound with nitric acid and sulfuric acid. So this is a nitration of the benzene ring. Now for aromatic compound reactions, there needs to be a super electrophile if the nitro group would be attached to the benzene ring. Now in this case, the super electrophile is in the form of a nitrogen double bonded to two oxygens. Now the question is, where would the nitro group add? Now remember that chlorine is an ortho director and fluorine as well, while this carboxyl group is a meta director. So you have two ortho directors and one meta director versus one ortho director, so that gives us no choice but to add the nitro group to this position, which is ortho to the two chlorine atoms and meta to the carboxyl group. Next is the reaction of that compound with thionyl chloride, which replaces the OH here with the chloride. Now for the reaction with thionyl chloride, one of the lone pairs of oxygen would attack the sulfur, breaking the pi bond, giving us a negative charge on the oxygen here. That negative charge would return, reforming the pi bond, kicking one of the chloride atoms. Now that negative chloride atom would attack the carbon, which bears the complex. As the chlorine attacks the carbon, the complex is now a good leaving group and leaves, giving us this compound. Next is a Grignard reaction. But the thing is with this Grignard reaction is that instead of adding to one of the carbons bound to a double bonded oxygen, the compound chose to bond with the carbon in between the carbons bearing the double bonded oxygen. So you have this carbon here, and this carbon, the double bonded oxygen, and this carbon, the double bonded oxygen. It chose to add to this carbon. So maybe it's because of the competition between the symmetrical oxygen atoms, the symmetrical structure that gave the compound no choice but to add at the middle point. So for a Grignard reagent, first we see the formation of the magnesium chloride where chlorine attacks magnesium, and then the carbon bearing the magnesium chloride, which is partially negative, would attack this carbon here. Now that carbon has a negative charge. It would lead to the creation of a double bond. Now this is extremely unstable, so it would easily deprotonate one of the sulfuric acid to regain its stability, giving us this product. Next is the reaction of that product with p-toluene sulfonic acid and water at 100 degrees Celsius, which leads to the loss of one of these groups. It's an ester. It's an ester. It has a double bond here and this CROOR, yes. Now first is we're going to this double bond oxygen here would be turned into a good leaving group by deprotonating first water and then p-toluene sulfonic acid twice, turning that into water. That water is now a good leaving group, so that would be kicked out, giving us a positive charge on this carbon here. rearrangement will lead to the positive charge being shouldered by the more substituted carbon. Now, the when there was a carbon rearrangement, the uh, whole group became a leaving group. Now, led to the attack of the oxygen in the water molecule because this is a positive charge. So that gives us a water atom bonded to that carbon. Now that water atom would then be deprotonated by another uh, water molecule, giving us this product. Now the butylene sulfonic acid will deprotonate one water molecule, which gives us this product here, and this oxygen, one of the lone pairs of this oxygen, which is bound to the main compound, would attack the sulfur in the butylene sulfonic acid, kicking off the water molecule in that compound, giving us this compound, which is an OTS. And then one of the hydroxide atoms, which was a former water atom that was deprotonated, would attack one of the hydrogens, which is attached to the carbon which bears the OTS, and that would lead to the kicking of the OTS since this is now a good leaving group. Now this would give the carbon here a negative charge that would deprotonate a water molecule, giving us this product. Next is the reaction of that product with triethyl orthoformate in acetic anhydride to give us an alkene here and an alkene and an ether here. So the mechanism goes as this: one of the oxygen atoms reaches to the carbon, the protonates that, giving us a negative charge. The ethanol would become a good leaving group in that compound. Now that negative charge would attack that positive charge in the carbon, which was the former reagent, leading us to this compound here. And then the oxygens of the newly bound molecule would attack another molecule of the main compound, which it would attack this compound. It would deprotonate another one of these, which gives us this compound here. And then the anhydride would deprotonate, leading us to the kicking of this leaving group and the formation of the double bond, giving us this product. Next is the reaction of that compound with 1-amino cyclopropane, which leads to the addition of the 1-amino cyclopropane. So first, the oxygen here deprotonates the ethanol, and that is now a good leaving group. Now the nitrogen attacks the carbon which bears the OH. Now we have here a positive charge on the nitrogen. So the protonated ethanol would reach out and take one of the hydrogens in the nitrogen, and here it would reform, becoming stable, giving us this compound. Next is the reaction with third butoxide in dioxane in reflux for 4 hours, which gives us this compound. Now being the bulky molecule, it would the third butoxide would have no choice but to reach to this hydrogen which is attached to the nitrogen, giving us a formal negative charge on the nitrogen, and that negative charge would then attack one of the carbons which bears a chloride atom, kicking the chloride atom, giving us this product. Next is the reaction of that compound with 2,6-dimethyl piperazine, yes, 2,6-dimethylpiperazine, to give us this compound. Now again, the nitrogen here would attack one of the carbons bearing the chlorine atom, so that kicks that off. Now there is a formal positive charge on this nitrogen atom here. Now the chlorine atom that was kicked out would deprotonate the nitrogen, giving us this compound. Next is the reaction of that compound with acetic acid and water and sulfuric acid to give us this compound. So that reduces this uh, ester here into a carboxylic acid. That turns rather. So the mechanism goes wherein the lone pairs of the double bonded oxygen with the protonate acetic acid that would lead to a formal positive charge on the oxygen, and then a adds water molecule adds once uh, the positive charge has been stabilized. The water molecule give adds giving us this intermediate. Now an internal protonation occurs wherein this O here would reach to one of the hydrogens of the newly added water molecule. Now this is now a good leaving group. Now good leaving group which gives us this intermediate. Now this intermediate here would reform the double bond so that there is a positive charge on the oxygen here, and then the water molecule would reach out and deprotonate the double bonded oxygen, giving us the carboxylic acid. And lastly is the reaction of this compound in palladium and carbon to hydrogenate the nitro group. Now, for simplicity's sake, I only showed the hydrogens that are needed for the reaction, and that I only showed the nitro group because the molecule is too bulky. So first we have the negative hydrogen reaching out to the oxygen here, and that collapses the pi bond, giving us this intermediate. The anion, the oxygen bearing a negative charge, would reach to a positive hydrogen, giving us two OH groups rather, bonded to the nitrogen. One of the OH groups, the oxygen, would reach to the acetic acid and deprotonate it, turning it into water, which is now a good leaving group. Now, the deprotonated ethanol, the ethoxide, would deprotonate the other OH, which leads to the reforming of the double bond here. Now again, the negative hydrogen would reach out to the nitrogen, and the oxygen would reach out to the positive hydrogen, giving us this intermediate wherein you have an NH and an OH, and an OH would reach out to the positive hydrogen, giving us a water molecule here. One negative hydrogen would reach out to the NH group, which would lead to the kicking off of the H2O of the water, which is now a good leaving group, giving us the amino group, which is now the final product. So that is it for this learning task. I hope you learned something, and thank you.